Part 6 of our PowerBI series. Today we are covering data modeling part 2. In last session we covered part 1. If you haven't watched that, I will highly recommend to go and watch that first. So before we begin, let me cover one of the example that we missed last time. So in our earlier session, we were trying to visualize the same measure, same total amount with the calculated column and measure. So the calculated column was throwing the wrong number. It was throwing something around 10 million. One thing I noticed was we didn't save some of the transformations, so that could be the reason. I calculated the same table again. If you look at this, it's the same table. We have the quantity, price we got it from the product table since we don't have it here. And we calculate the total amount, which is quantity multiplied by price, which we have represented here. If you see here, we just took the sum of sales from total amount. From sales table, total amount, we took the sum and it rounds to 52.84 million. And the same one, we used a measure. We use this measure, sum x measure, which is a iterator. It iterates on the sales table and it gets the relevant price from the product table and sums it up. So this is a measure, right? This is a calculated column, so both will show the same results. And we also saw the direct query where we created a measure. It was giving us the same results, right? So just wanted to clear this before we proceed to today's discussion. Okay, coming to this part 2. So let's recap the what we have discussed in our first session. So two important takeaways in first session are referential integrity. So Power BI assumes referential integrity for one-to-many relationship. What is referential integrity? Ensuring every record in table A has a reference in fact table or the other table. If you look at this, for each record there is one or many references here. But for it is missing. It is missing from the left hand side table. So Power BI virtually adds a blank in one-to-many relationship to assume the referential integrity. All the non-matching keys from table 1, it will create a blank and maps with that. So Power BI by default assumes referential integrity for one-to-many relationship in import mode. And if you come to many, if you see this for 5 and 6, there is no reference here. And for every record, there are multiple references in the other table. This is called many-to-many relationship. If you look at this, in from left hand side table, whatever the distinct is, they are represented here 1, 2, 3, 4, and the respective count is there. But in total, if you look at this, the total is different. When you sum this up, it comes to a 8, but the total is showing up 12. And is it a wrong number? No, it isn't, right? We are doing a count on the second table, this table, and there are 12 rows, so it's showing the total 12. But user may get confused, right? So he may confuse what are the missing numbers. Either there are two ways to fix it. Either you fix rows or either you fix the totals. Okay, so there are two ways to fix it. One is you can fix the rows and show the non-matching rows and the totals. Let's fix the totals first. If you notice one thing carefully, why we are missing these numbers? This is trying to visualize whatever the numbers are there on the left hand, and it is showing up the count from the right hand table. And there is a count for 8 things which have some reference here, and there is a 4 things which are remaining which doesn't have here, right? This doesn't have anything. So to fix this, to fix the totals, if we go to the table and if I go to the visual, if I select is not blank, boom, you see this? So whatever the measure, or it could be anything, it could be any number that you are taking it from the second table. If for all the rows which have no reference in the first one we are referring is not blank. If we, whatever the values that are there on the left hand side, we are counting only them. If you see the total, earlier it used to be 12, now it is 8 only. The reason is we omitted the numbers which don't have matching keys in both the tables. This is correct. Now you fixed it. But is it correct way? No, because it is not the right interpretation. There are 12 numbers, but you are showing up only 8. The remaining 4 are missing. Right? This is not the ideal fix. The ideal fix is to fix on the rows level, which is our first method. Right? Let's go that. Let's go and look at that. To do that, there is a concept called bridge tables. So in data warehousing concepts, we call it as a role-playing dimension. What does it mean? Let's go back to data view, model view, and see this. So if you look at these, one second, yeah. If you look at this, there is a straight relationship from table 2 to table 1 many to many. Now I want to introduce one table which will have this many to many relationship. I want to bring it like a many to one and one to many, right? I just want to have a bridge table in between rather than connecting them directly. Let's see that. So there are different ways to do that. One way is you can do at the source. If you have the tables from Excel or something, you can do it in the Power Query as well. If I go to Power Query, let me right now, since there are only two tables, I'm gonna append them. Append means adding them vertically. First table would be table 1 many. Second table is table 2 many. I just added them. Now I have to remove the duplicates. Okay, let's call it as a bridge M to M, etc. Let's bring it here. I'll delete this relationship. I'll make a relationship with the both the tables. Now I took the values from this table, table 1 many, but and counting on table 2 many. If you see that there is no relationship, this table can filter this table can filter this, but this table directly can't filter this, right? There are different ways to tackle this, but let's not go into that. Now let's use the value that we brought in from bridge table. Instead of column 1 from table, I'll just take this. Now you see the counts are fixed. There's nothing missing. In the model, there is a reference for 4, 5, 6. We are showing, 5, 6. We are showing that up. We are not missing anything. This is how you need to, you can fix it. And if you go back and recap what we did, there is a many to many relationship. We broke it down into one to many and the other one to many. So by combining this, it will become to many. These are called as bridge tables in Power BI or role-playing dimensions in data warehouse. So this is how you can do that. This is one lemon example, right? And here, if you notice this, there is only one column, which is a common column joining this. There could be two different dimensions altogether, right? Let's look at one business example, and which is from this model. If you look at the second one, there is a many-to-many relationship between a products to sales agent. If we go back to the data, Let's unhide them. Let me hide the other tables that we have so far. So we don't get with confused with too many tables. Even in real time, whatever the tables that you don't want to present to users or someone who connects your model, right? You can hide them here. So if you go to data view, we have a products table, we have a sales table. If you look at the products table, there are many products and the different product IDs. One product could be sold by multiple agents. Same, one agent can sell multiple products, correct? So when we join between agent or product, between these two tables, it will create a many to many relationship. It makes sense, right? Now go back to data and try to visualize them. If I do agent by product count, if I want to count the number of products that each agent sells, this is how it is showing. 3, 3, 2, 8. It makes sense. And if we go to agent table, if you select here and see there are four distinct values, but we are visualizing only three. And if you look at this agent 3, Nilo for Ravel, he is not selling any product as of now. Tomorrow he could sell some products, right? And if you look this in earlier example, there was only single column and the common column is same. Now if you take, there is a agent ID, there is a product ID. So if we want to build a relationship, we have to have a bridge table which has the details related to agent and product. Then only we can build the relationship with both of them. Let's implement and see that. And if you remember, our main agenda is to make one to many. All right, so there is a many to many now. So our agenda is to make many to one and one to many. So if we combine them, it will become many to many. That's our agenda, correct? So to make that, the dimension tables, whatever the dimension tables, they should be unique when we deal with the multiple dimensions. If we go back to the data and see the sales table, the agent table, it has a multiple references. Okay, and same way, if you look at the products table, it has the multiple references. Here, our agenda is to make it a one-side table and create a bridge table which will have the references for both the keys. Two things. First, let's go and build a bridge table. So I have already done that. So I'll explain you how I did. So I took the, since I need to clean up the products and sales table, and if I do a transformation on top of it, I can't do that, right? I can't get all the required columns. So I just took a duplicate of them. I just took some dummy references for both of them and I created a bridge table. I created this bridge table. What I did, I take two tables in account and joined based on the agent ID. I did a inner join because I just want to have the references that are common to both of them. And I did an inner join. After that, I expanded the table and only took the agent ID. I just need the IDs, right? I just need the matching keys in my bridge table. I don't want to overcomplicate it. So, and I removed all the other columns. I just kept these two and I removed duplicates on top of that. So it gave me the uh, distinct foreign keys. And this column has all the references that are available in the first table, which is the sales table, sales agent table, and this has all the references related to product ID table. Okay, if I close and apply, now I built a bridge table between these. Let me delete it and create a bridge table. So if I, this is a product table. If I join the product, it will create many to many. If you, and there is one reference, that's why it's not showing up, but let's do this. Let's create agent and agent. It is creating many to many, but our agenda is to create many to one, right? We are trying to solve many to many, and again, if we introduce many to many, that doesn't make sense, correct? So what we need to do is we need to remove the duplicates from the this dimension table, sales agent dimension table. Let's go back and do that. I came here and this is a sales table. I don't need a product reference. I already have it in our uh, bridge table. Uh, Here I want to delete the duplicates. Okay. And then products table, same with products table. I don't need agent details in product table since I already have it in my bridge table. And remove duplicates. Removing duplicates, you should be careful. Since I'm pretty confident that they are unique, right? That's why I'm just selecting here and deleting it. If you are deleting on the multiple columns which are different, then you should be very careful before you delete them. So if you have any confusion, if you wanna remove distinct, then select everything and remove duplicates. That makes the job. Okay, now I have only products. On products table, I have only this distinct products, so I can create one-to-many relationship. I join this product ID to product ID. I join this this agent, right? Agent to agent. Now, if you see this, we successfully break down the many to many. There's one to one because there is not that many product references here. Even if we have them, then it will become many to many. Okay, so you can ignore that. Now we successfully break down many to many into many to one, and or let me add one. I can add one more thing, but yeah, we can ignore it. If I go back and visualize, this is broke down. So to do that, this is basically product by sales agent. If you look at product by sales agent, so we took the product from here, sales agent from here. It can't flow that side, right? It can't reach this end. That's why it's not filtering. You assume this. So product is here. It will go and filter bridge table, and bridge table can't go there and filter this, which is a count from this table. If you look at this, the count is coming from agent ID table. See here, it's showing all because it's not able to filter them. How to avoid these things? There are three ways to do this. One is you can use a bidirectional filter. Second one, you can use cross filter, which is a DAX function. Third one, you can expand the table. There's a concept called expand the table. Again, it is using DAX. These are the three options you have. Let's see all of them. Let me duplicate this. Okay. So I have duplicated this one into three different things. You can see them at the bottom. Now my aim is to fix it in a three ways and show them, and at last I'll talk about the best way. Now the first way is to enable the bidirectional. Since this table is going there and it is not able to filter this because of this relationship, there is no relationship from bridge table to sales agent. There is only from sales agent to this one. There's only one way, right? I'll just make it two way, both the cross filter direction. Now if we go back and look at this, it is able to filter now, right? It is able to filter the agent count. And if I come back, and this is one way, right? I'll switch it to single only. And the same thing, this is the first way. You can directly enable the relationship to bidirectional. And second way is, if you do this, sometimes it could create the ambiguity. If there is one more table which is connecting to products and sales, okay, then it will create a circular dependency error. So sometimes you can't enable bidirectional. At that time, what you can do is you can leverage the same in calculation level. Let's see that. So what I need is a count of agents. So let me create a calculated column, new measure, agent count, count of agent ID and many to many sales, right? Let me use that here. It is showing 4 because, as I said, there is no propagation, there is no filter for this one, which we earlier we enabled bidirectional, right? Now let's do through a calculation. Let me wrap this in a calculation. Calculate function. Why do we need to this? We will discuss in DAX sessions. Now there is a filter. There's a function called cross filter. So it asks you the first table, which is on the left side. It should be sales agent many to, we are supposed to give the table name, I mean column name, so agent ID, and the right side column name, which is a bridge table. What is the direction? We need both. Look at the measure. It is split into different things, right? So what happened here? So earlier we physically changed this. We changed this direction. We changed the direction to bidirectional, single direction to bidirectional. The same now, and there was a limitation, right? So there was, if there is a circular dependency, then we can't enable it. PowerBI can't have a circular dependency, right? So in those cases, you can leverage DAX. You can go here and write enable the directional bidirectional at a cross filter using a DAX function. There is one more concept called table expansion. So this one we will discuss more in DAX, but I want to introduce you here. What does table expansion means? Count by table expansion. And calculate count of So we need a agent ID, and we have to expand it to the bridge table. We use this measure here. Okay, we are trying to visualize from product table. So I think it's a bridge table. I'm doing different thing. Now you see the breakup, right? So it is divided into multiple things. What happened? So we are expanding this table, whatever the calculation that we did this, we are bringing it to here. We are expanding this calculation to the bridge table. Let's say, let me go to my notepad and explain it. So there is a bridge table, and this is the calculation. This is the how it is there, right? Sales, agent, many to many. So we are trying to visualize from this side. We are going from product table to this table. Whatever we filter, it can reach this table because there is a bidirection. So this product filter could reach here. And from there, it couldn't reach this, right? The count of here. Because there is only one direction, which is from sales agent to bridge table. What we did is we expanded this bridge table to this calculation. Behind the scenes, it will add like a virtual row with the count. So we expanded the table, right? We expanded the table to the measure we have written in a calculation. This is called table expansion. When we did that, the count is available here and it is able to filter from here to here. Now it can filter the details. So if I go back to this one, let's look at the calculation quickly. So we are taking the agent ID count and we are expanding that count to bridge table, which is here. Here it will add a virtual blank or virtual column, and it can filter that column because it is already expanded. It is not reading from here, it is reading from here directly. So this is table expansion. So we did it in three ways. Right? We did it in three ways. This. Now, which one is the best? If you go back to Notepad, the first one, if you don't have any circular dependencies, if you don't get any ambiguities, prefer this one because you no need to enable it in every calculation level, right? So I prefer this one if there is no ambiguity, and if there is ambiguity, maybe you can go with either of the option. If you expand the table, you don't need to filter anything. All the filters that come to bridge table, it will automatically filter the calculation if there are many filters. If you look at the cross filter, we enable the relationship in a measure way, right? We enable the relationship between two tables virtually. If there is another dimension, let's say if there is a date table, date table to date table to this one, or date table to this one, It can't filter. If there is a relationship between date table to bridge table, we can't filter it, right? Because there's only this direction. It is in this direction. You can't filter this to this if you use a cross filter. Whereas if you use bidirectional, it will filter here, it will filter this place, right? So bidirectional, it will enable it. If you use it a cross filter direction, it will only stick to that bridge table and this, because we enable between these two only for that calculation purpose. And if you use the table expansion, it works the same. If you use the table expansion, it will come here and it can filter this. So 1 and 3, these two methods are optimal. One is best because if we just change the direction, we don't add anything extra, right? That's why it don't take much memory. So one is best, and if not three, if it is just for one calculation or one measure, go with the cross filter, this second option, one type thing. Okay, so that's it. And if we carefully notice it, and even here, if we notice this, the actual count is coming, but there are four agents, but we are showing up three. How to fix that in these situations? If you look at here, let's do that. Let's do that, and we can move to the next one. If you see this count is coming from the many to many product ID. Let me create a new measure. Order count. Order. We use the same measure. It gives the same count because we are not doing anything extra. But if we do something like plus 0, what we externally forcing the count with a 0 wherever there is no reference, we are telling to take a 0 there, right? You can write it in two ways. You can write a is blank function. If it is blank, then show count, otherwise show 0. You can write that way, and this is one of the simplest way. If you do this, wherever there is no reference, wherever there is no count, because this Nilofer Ravel is not selling any products, right? That's why it was not showing up. It was showing only the common records that are available. Now it is showing up the 0. This is how you can fix it. Okay. And one more takeaway from this is, if you look at this table, if you look at this, one product is selling by different agents, right? And if you sum up the total, it's becoming 3. It is supposed to become 6. Why it is becoming 3? Because there are only 3 agents who are selling the products. Or you can do the reverse way as well. You can take the agents and take the count of products. If you look at this, there are each product is selling by different agents. If you go to data and look at that, if you go to bridge table, if you look at here, this product 1 is selling by 4, this 2 is by 4, this 3 is by 1. For every product there is 1, right? So for 6 products there are only 3 distincts. If you look at here, there are only 3 distinct values because there are only 3 agents who are selling the products, right? That's why it is showing up 3. So is it a mistake? No, because each product is selling by one each product is selling by one agent and there are total 3 distinct agents. This is correct only. But how do you explain this sum to your users? right? This is something called a semi-additive measure. So you will see that there are different things. If you take a number, there are three things called broadly two things. One is additivity, and the second one is non-additivity. So within additivity, there are semi-additivity and non-additivity. So let's take an example and try to visualize that. Let's say let's assume a table which has date, and for simplicity we can take month. April, May. There are different stores, store ID 101, 102, 101, 102, and the sales amount 500, 600. Okay, quantity sold. Okay, let's look at the closing inventory or closing stock. And take the customer rating for that store as well. Let's take this measure, quantity sold. If you sum it up, it will become 100, and you can slice by anything. You can slice by a month, you can slice by a store ID. If you slice by month, the quantity sold in that month will be 30. If you split by May, if you filter by May, the quantity sold would be 70. If you split by store ID, the quantity sold would be 40. By store ID 2, it will be 60, this 2, right? So you can slice down this measure by any way, right? It can be sliced by all the dimensions, right? So quantity sold can be filtered by any dimension. If you take the second one, which is a closing balance. If I ask you what is a closing balance now, what do you say? You can't sum it up, right? This is the closing balance in April. This is not the current closing balance. If I ask you the current closing balance, you go to the maximum month. This is the latest month, and you will sum up these numbers, right? You will sum up these numbers. So, second thing, if you take it, closing stock can be defined at month only, right? You can't tell me all the closing thing, right? You can't tell me what is a closing. If you sum it up, it will become 130, 170, 200. Is it the closing quantity you have? Is it the stock you have? No, right? That's an incorrect calculation if you do that. So let me take one more example. Rating. If I ask you the rating, do you sum it up? If I ask you store one rating, if you sum this up, 9.5, it doesn't make sense, right? So for these kind of things, you have to do a different formula, like a 4.5 is the rating. This is for how many customers, plus 5.0 is the rating for how many customers, right? Divided by, this is 101, this is 102 customers. So 101 customers plus 102 customers. You have to derive something like this. You can't simply slice by any dimension because you can't slice it. You are defining a different formula and calculating the average rating. You can't simply calculate and say 9.5 is the rating, right? These are wrong. So you have to do like this. So the measure quantity sold, you can slice by any dimension. So which is means you can add those numbers and slice it by any dimension, which are called additive measures. If you look at the closing stock, you only can slice by month, right? If you want to know the status of the closing balance for store one, you have to further slice, based on 101 and get that. You can't simply add it, right? These are non-additive measure. Within that, these summit you can do at a month level, which means you can do this closing stock sum at month level, but not at a product level or a store level, right? These are called semi-additive measures. You can't slice it by every dimension, but only by few dimensions. That is a semi-additive measures. Non-additive measures, you can't sum it up. You can't sum them. Here you can sum them. Here you can partially sum. Here you can't do. You can't do any sum. You have to depend on a custom formula. These are a non-additive measures. And if someone asks you, if your user come and ask you, hey, what is the difference? So there are total number here, there's total number more, but it's showing the count distinct, only three. You should be in a position to answer. You should be in a position to justify this number, right? Otherwise, people will confuse. So you should explain them. This is how you need to do this. In the earlier case, we have to fix that. There's no option because there's some piece of information which is missing. So you have to fix that. Here, you no need to do any fix. It is how it is. This is how we need to analyze, right? Because there is many to many relationship, and this is how it is. So you have to be in a position to explain this. So how you can do this? I just told you, right? This is a non-additive measure. That's why I mean this is a semi-additive measure. So you can't get all the count, right? So you can just do it in that way. That's about additivity, semi-additivity, and non-additivity. Now let's move to the other concept called a normalization versus denormalization. Normalization. Okay. So what do you mean by normalization? So normalization is the process. So we use this process and we store the data in different tables. What is denormalization? So by combining many tables, if we make them a few, let's say if there are two tables or three tables, if we combine them and make it as a one table, is a denormalization. If there is a one table, if we make it into two or three tables, this is a normalization. This is denomination. Let's see one example. If we go back and look at the layout one, which is a sheet one. If you look at sheet one, there are different things. So there is a sale date, there is a quantity, there is amount, quantity. These all are the facts, right? If you look at the name, there is a client name as well. So there is a mobile number, customer name, customer mobile number, customer address. We have only one table. There's a product name, product category, price, store name. Everything is in this fact, this one table. There's only one table. If you want to make it a dimensional modeling, if we do the transformations and make it like this, right? I splitted the customer table, I splitted the product table, I create different table. I only put the references in here. If you see here, there's only product ID. There is no product, other product related information. Everything is available in product table. If you look at customer ID, only customer ID is here. All the customer related tables are details are here. Customer ID, address, mobile number, everything is here. What is the benefit of this? The benefit is that you reduce the redundancy. What is redundancy? Storing the same data in multiple times. If you look at here, the store name, we are saving it multiple times. The address, if a customer purchases, if a client purchases one product, we are saving his address every time, every single time. So we are duplicating the information. What happens if we duplicate the information? It will take more storage, right? If you can recollect our first session where we talk about the resources consumption, so because of taking it more strings, it will take more space and it can't compress. So for search or for any operation, it will take more space and more time eventually. So this table, converting this table into this kind of dimensional modeling is a normalization. So we normalize the process. What is the benefit of it? You can save it. You can save lots of space because you are reducing the redundancy, which is a duplicacy. And if there is something to update, there is a customer address change, you can go here and update here just the address. In previous case, with a single table, you have to go to every transaction and update the client address or customer mobile number, right? That's the advantage. There are lots of advantages we will discuss, but the process of making this one table to different dimensional fact tables, many tables, is the process of normalization. What is denormalization? Reverse. If there is this kind of model, if you make it this, that is a denormalization. Denormalization is making multiple tables into one table, basically combining the tables. What is the advantage of this? Assume that you are connecting to your data in a direct query. Direct query should be executed by tables, right? I mean sorts. If you frame these kind of queries, if you want to visualize product by customer by sales, it will do two joins with the sales to product and the customers. It will create a big join with the two tables, and it has to perform on top of these three tables in your database. Power BI frames the query, right? In our earlier session, in our part one, I have shown how Power BI frames the query. So it will frame you the query and it will show you in the results. But the source will take more time because there are more joins. Instead, if you have a simple table like this, you can simply query this table rather than having multiple joins. You will just go and query on this table and get the results. This will be fast. Wherever you want the retrieval time very fast, right? So you follow this. That's one. It is not only for direct query. Even if you design some web applications, if your SQL has to bring that, if your query has to bring that, it is preferable rather than executing these giants and all. Okay, so let's compare the differences, broad differences between these two. If you look at here, If you take about the performance means if you take direct query, if the source has to execute a query, then normalization works best because there are low joins. It doesn't need to do a join operation at all, right? If you look at denormalization, it is faster for reading for due to fewer joins. So normalization, right? Because there will be many tables. If it needs to combine all the tables and frame the query, it will become a lengthy query and more joins. To operate it on source, it will take more time, right? That's why it's slower. In denormalization, there is only single table. Here you will be having different dimension tables. Normalization, denormalization, simple table. You no need of any joins. You just go there and directly query. It will be fast. Data integrity. Data integrity and data redundancies. It is high integrity with a low data redundancy or no data redundancy. You don't duplicate it, right? You don't duplicate the same efforts everywhere. Here, there will be lower integrity and increased redundancy. You are repeating the same information again and again at transaction level. So it will be smaller in file. If you look at the fact table, it only stores the keys. Customer address, it will only store one time in customer table and it will take all the keys in a sales table. Only the keys are repeating here. Whereas it here the entire address is repeating. So strings takes more space and we are repeating the lengthy strings every time. So it will definitely increase the file size. And even the search time. Within that, if you want to search the different vendor addresses, it will take time because searching strings takes more time. Model complexity. If you look at very high level, this sounds like a more complex because there are multiple tables. You have to understand the relationships, what is the relationship, and then you have to understand the data. Here it's a very simple to understand. You can just go there, single table, you can easily understand. And maintenance, it is very easy to maintain. If there is any change, you just change in a customer. If there is a customer mobile number, change in customer mobile number, you just change in one place. Everything gets updated. Here it is very harder. You have to change in all the rows that are available. You have to change in multiple places. So when do you go for this? Suitable for transaction systems. If you look at a database level, it highly suitable for transactional systems as well. Systems. And if you look at reporting, don't confuse with the reporting. This is for direct query reportings where you directly query and where you rely on the source. You rely on the source and do analysis, right? So at those cases, this comes in handy. If you use tools like Power BI, which are like aggregated tools or Tableau, anything, right? So they compresses the data. So there, these kind of models prevails. Especially Power BI is highly optimized for star schema or dimensional modeling rather than a single fact table because it compresses in a vertical format. It compresses each row and stores it. That's why if you load a 50 GB table in your database, it could be compressed to 4 or 5 GB in Power BI. So, and the next one, this is an example. We have discussed the same. So, single table versus query design. As I said, multiple joins are required. Here, only simple table directly query. So, maintenance is easy. We have already discussed that it will be increased maintenance due to data duplicacy and more flexible to handle the complex calculations. There is a thing called context, which which we'll be discussing in DAX more and more. Without that, you can't crack the DAX. If you want to build complex calculations, sometimes you want to hold the context on one dimension and calculate the number. In those cases, it will be less flexible. If you have single dimension, it is very difficult to manipulate the DAX. It is very difficult to manipulate the calculations. If you deal with the dimensional modeling, which is like normalization process, it is very easy to do that. So these are few disadvantages and advantages of going to normalization, denormalization. So if we confine to Power BI, I highly suggest to go with the normalization process. For if it is import mode, definitely go with the normalization process. And if you want to go with the denormalize, it should be a direct query with a heavy joins. If your data is going to be heavy joins, if it is going to be join more dimensions and complex joins, then denormalize to an extent and work on it. So this is different use cases, and live connection, it's pretty more or less equivalent to import, but in import you do all the modeling in your Power BI. In live connection you do in some analysis service. I prefer to go with a normalization even for analysis services. They are highly optimized for star schema or dimensional modeling. Okay, I'm sorry for that. Yeah. Now, we have seen lots of things like we have seen how to handle many to many, how to handle one to many, and we have discussed lots of things. Now, so far, whatever the examples we took, there have only one fact table. What if we have two fact tables, right? Let's talk about that. If you have many fact tables, multiple fact tables, what is the possibility? There could be relation between facts. There may be no relation. If you talk about no relation, let's take some, there's a product dimension. So you are selling few products, right? There's a sales table, product ID, and quantity and other details. And you are not the manufacturer. You are just selling it, right? You are purchasing it from different people. So this is a purchase table. So what is the product ID? How many quantities you purchased, date, and etc. etc. Okay. Now this is your product table. Your product table is connected to purchase table. Your product table is connected to sales table. But there is no relation between your purchasing table and sales table. These are independent facts, correct? So it is very easy to handle because there is no relation between them. So one table will not scan the other, and you can leverage the product table, which is a it is just like a for one product there will be many products here, right? It will be like a many to many. But there's a bridge table, which is a product table. It's just like your many to many scenario, but there's a bridge table, which is a product by default. So the analysis becomes easy, and we have seen this case, right? So I'm not gonna talk about this. Let's say, let's look at the first example. If there is a relation between two fact tables, let's take one example. You see lots of outlets. It could be Levi's, it could be any brand, right? So they will announce flat 40%, flat 10%. How do they give you? If you look at one of the invoice, or it could be any hotel. So, or any order from Amazon or Flipkart anywhere. If you look at that, it will have order ID. Within order ID, there could be different products. Product A, product B, product C, and they will do the total. And they'll say flat 10% off, which is 100. The total will be 900. This is how a typical invoice looks like. It has different components. One is this is an order which has multiple products. Within order, you have multiple products, and you also got the discount. Did you get discount on each product? No, you got an overall order, discount on order or total amount, right? If you have to save this, and in every store there could be multiple orders. Within one order, there could be multiple products. If you have to have a fact table, you will be having a orders table with all the order IDs, and you will having the discount amount as well. If you look at the products table, you will still have order ID and you will have the product ID. If this is invoice is 1001, there will be only one reference. It is entire thing is an order, right? Here, if you look at this, this will have 1001 product A, B, C, the respective price, and if you purchase the quantity, it will have the quantity, and it can't have discount because discount is at a order level. It is not at a product level, so it can't have a discount. And if you visualize, this will be a one to many. Okay, now let's look at that. You can't assume this as a dimension table just because of this one. Why? It has some factual information. Discount amount is a fact. It is not a dimension. Let's go back and see this model. So this is a model. If you see, there are different stores, there are different customers, right? So customer information will be available in orders table, and date, when is the order, the date is available here, which store it is available here, and the product details, which have the different line number. You see the line number, right? For every order, there could be different lines. In one order, there could be 100 lines as well if you purchase 100 in one order. And the product information is not here, which is here. If you see this is here. And the promotions, the discounts, all the relevant information is here. It is not the discount directly, but you could run different campaigns, right? It is that information. Now if you see this is, you can't call it star schema as well, because if you see, all the dimensions are directly connected. But the fact table, this is not a proper star schema. The fact table, this orders fact table is connected to this product details by order fact table. Let's say if I want to get the total amount for a product, there is no total amount here. First, I need to come here and collect the total amount, the unit price by quantity. I can do this. I can get the total amount. On total amount, I need to deduct the discount, which is available in here. For every order, there is discount available here, right? I need to deduct that and show the results. If I want to filter by customer, this customer table should come here and filter all the products, and all the filtered information here should go and filter this big table again, which is fine. This can filter this, though it may take time, it can filter this. But what if I need to slice by product ID? Product ID can come here and it get the information here, but it can't go from here to here, right? The direction is in one side. I can simply do that. We just learned that we can enable both. Since there are no ambiguity, this is not connecting to this. If it is connecting to this, we can't enable this. But so we can do this. It will filter here. If we wanna do the related customer table, customer counts or anything, we can't do because it is filtering here. All the product filter can come to here, but it can't go. We have to again enable the bidirectional. Even if you build model in that way, it will still take more time because of the multiple scans. What can we do? We can apply the denormalization here. So what is the facts that are missing from this table? That is a total discount. Let's go back to our notepad and see. So before you build any model, I highly suggest you to go and understand the business first and then understand the data. Go to each and every table and understand the data and understand the redundancies, if there are any redundancies, if there is any duplicacy there. Just understand that and then build a model. In this case, if you carefully look at it, you simply can't do a join and get the additional tables here. Why? I'll tell you. For one ID, if we directly get the discount amount here, let's say the discount is 100, right, for this order. If you bring the discount based on the order ID, so the order ID will be same for all these three. So it will come 100 as here, 100 here, 100 here. So if you take the price 1000, if you sum the discount 300, 700 will be the total amount, which is a wrong. How do we do that? You have to first take all the amounts, this 1000, and bring it here. Create a calculated column, total amount. If you bring it here, 500, 300, 2000, you submit here. You can use related table DAX function and get it here. I'm just explaining in DAX way. You can do in M language, you can do in a SQL as well. The best way is to do at the SQL at source level, if not at M code, if not in DAX. So as close as source, we discussed this right in our earlier sessions. If you have any transformations, do it as close as to the source. Okay, but for simplicity, I'm just explaining you, and we'll come back to that. Now, if I make this 1000, if I calculate a new column called percentage of discount, how much? What will be the discount percentage? 100 discount amount by total amount into 100, which should be 10%. Now, instead of discount amount, if I bring the discount percentage to this side, let's say this called discount percentage. 1001, it is 10%, 10%, 10%. I'll not bring this column, discount amount, I'll bring this one, discount percentages. Now, if you calculate now, the total is 500, 300, 200, which is 1000. What is the discount percentage? 200 of 20%, 10%, 20. 300 of 10%, 30. 500 of 10%, 50. 50, 30, 20, which is 100, which is giving the right number. If I do this way, if I can get the percentages here, I can eliminate this table. I no longer need this table. If I can bring the percentages here. This process of eliminating this table by getting all the relevant information here. It's not you no need you won't you not only get the percentages. If you just get the percentages, you will miss the relation with other three dimensions. If you look at this, you will miss the customer dimension because there is no customer key here in product details table. You'll miss the date reference. You will miss the store reference. So along with percentages, discount percentage, you will bring the other table references as well. You will bring the customer key, date key, and product key. So along here, you will bring four things. One is percentage info, and second one other keys from order related dimensions. Now I have already done that. I have done in SQL. If you go layout, now you see the right. I just called the denorm because the process of combining two tables into one is a denormalization, right? That's why I just call it as denormalization. So if you look at this table, I'll show you what I did. I intentionally brought two other fields as well just to show you a difference. You see, I have written this SQL code and brought all the tables, all the relevant details. And I successfully eliminated two fact tables into one fact table. Now if you look at it, it looks like a perfect star schema. Every dimension table is connected to the one fact table. So there is no relation to this fact table with any of the fact table. Now the model has only one fact table. So this versus this is the best model. Are we done with this? No. After merging this, we have to be careful about the calculations. You should know the data. You should understand what you did. Let's say example, from this model, if I want to take the orders count, I'll take it from here. I'll go to orders number and I'll take the count. If you look at this example, orders PC, order number. I just take the count. It is enough for me. If I alter the model, if I simply, this is the denom order count. If I simply take the count, it is 10k. Do I have 10k orders? No, I don't. I have only 100 orders. If you look at here, orders PC, the distinct orders are 1000 only, 100 only. And if I go to denom table, if I check the order number, even the distincts are 100. There are 10,000 rows because one order have multiple products. One order have almost 100 products. That's why it is showing up that number. We are taking just count. If we are calculating on denom table, we have to take the distinct count. So it is not just building the model, but you have to be aware of the model, how you have saved. And if you want to get the total sales amount, all right, if it is with the denom table, you just go here, you multiply by quantity, unit price, and you shouldn't. I intentionally brought these two columns. You can't calculate total sum in this way. If you directly look up from orders table, for every order ID, the total will show this. If you sum it up, from one order ID, there are 100 products. It will sum up 100 times, which gives you a wrong number. It could be a discount, it could be amount, anything. You can't do in that way. Instead, we bring these percentages. When we need a total sales, what do you have to do? Quantity by unit price multiplied by 100 minus this percentage. It gives you the total sales sum. You have to write calculation in that way. If you need to write the same calculation in old model, this model, you have to write a lot. You have to do in one variable, you have to do sum x, bring all the amounts here and take the next amounts, take the discount amount in one more variable, deduct them and get the amount. Still it will not be filtered by these dimensions. You have to enable the bidirectional. There are more complexities with this model. Whereas this model, you don't need to enable them. You can just write simple calculation, sum x, this column into that column minus discount. So it is very easy to write the calculation as well. So by denormalizing, you are writing the calculation simple, right? Here you have to write more calculation, complex calculation. Here you will write simple calculation. This is one model, but in real time you could face lots of models. How do you master them? Just by practicing and just by applying your mind. Think of it and try to reduce the redundancies. Try to make it as less many tables as possible without redundancy. You can't repeat it. This normalization is an see we break it two dimensions, two fact tables into one. We can further reduce all the dimensions and make it as one sheet. There is also denormalization, right? But that gives us the adverse effects which we discussed with a single fact table. Denormalization good for Power BI, but to an extent. You can't denormalize completely. That is not good. And this case, it didn't rise good because we did it to an extent. We just confined to fact tables. We reduced the redundancies and all. We, instead of saving that order information multiple times, we have created few columns here and save. Easy for calculations and all. This is how you build it. And just get more data sets, practice on it, you will master it. And that's about the facts. Let's move to the dimensions. We have discussed about the facts and dimensions. There are different categories of dimensions. And I'm not going to cover all. I'm just going to give you very high level introduction to different types. One thing I would like, and if you look at the bridge tables, they are one kind of dimensions only. They are called role playing dimensions. Before you analyze, you will go through the factual information for sure and you will understand it. And I highly recommend you to go through the dimension tables as well. So don't neglect dimension tables because there could be different varieties of dimension tables. I'll talk one or two in this session. So we have already discussed bridge tables, right, which is a role-playing dimension. Let's talk about slowly changing dimensions. Let's say you have a customer table, customer dimension table. You will have customer ID, customer name, mobile number, address, blah blah blah. Okay. If you have any promotional offer, you will leverage these customer mobile numbers. You will send them the promotional offers. Hey, we are having this offer. You can, this is the cutoff time. You can come and purchase and avail this offer. So they can come and use that offer. Your business will grow. Your sales will grow, right? And there are different ways. Let's say my customer ID is one. I am Bharat. My mobile number is something. Address. I may change my mobile number. I may switch to the new address. Correct. If you are delivering the goods, if you deliver to this address, no one is there to pick up once I change the address, right? So for that, these things for a dimension, for a customer dimension, there are few attributes which could change over time. If they change over time very frequently, they are called rapidly changing. So in this case, the dimensions slowly changes over time. I don't change mobile number every day, right? I don't change my address every day. That is not possible in real time. So these dimensions will change over time. Few attributes of these dimensions could change over time. How do you save them is the challenge. If you, there are multiple ways. There are things called type 0. Type 0 is basically you don't change it. You don't save any record. Whatever you take, you'll just have them. You don't change it. This is a bad thing, bad practice. If I change the number, if you send the promotion, it won't reach your customers. The second one is a type 1 dimension, type 1 SED, which is you simply overwrite. If my number is 9 something 1 2, if I change it to this, you will remove this number. You will only save this number. You remove this and you will only save this number. If I move to different address, if I move to different city, you remove that. Let's say I moved from Hyderabad to Bangalore. You'll just simply save Bangalore. You'll remove Hyderabad. This is type 1 slowly changing dimensions. There's type 2. This type 2, they add a new record. Let's say there's a Bharat 1 with this phone number. If he is moving to it will make add one more one. Same customer. His number now it is this one. Okay, he moved to Hyderabad now. It will maintain two records for the same dimension, same customer. These are called type 2 SCDs. And there is one more thing called type 3. There are type 4, 5, 6. I'm not going to cover them. They are mix of these earlier versions, so I'm not going to cover them. Here, you don't add a new row. Here, you will add a new row, right? Here, you will add a new column, like a mobile number, and you will add a previous mobile number. Previous mobile number. Okay, it will not manage two records, it will manage only one record. Okay, if I change it, it will take this into here and it will replace this mobile number with the current one. So these are different. These are called type 3 dimension, type 3 SCD. One limitation of this is you can't create column every time. Few customer can change one time, few customer could change 5 times over a period of 5 years. So if you go by row, you can add anything. In columns, in these kind of type 3 dimensions, you will save relevant information, past one change or past two changes. Okay. Let's ignore that. There are type 3, type 4, 5, 6 and all. You can go and read them. So the important fact that you notice is when if the dimension is type 2 dimension, if you bring it to in your Power BI and if you create with your fact table, it will create a many to many. So because there are multiple dimensions, so first I have the Bangalore address and I have the Hyderabad address. That's why it is making duplicacy. So customer ID, I could be purchasing right different products. So it will make the duplicacy. If you create like this, it will create many to many. You can't go directly and create a bridge table and all. You can't do that because you can eliminate the dependency. You can eliminate it for analysis, whatever you need. You can transform the data how you need and you can take the distincts. Instead of doing a bridge table between fact and this one, you can eliminate the duplicates here. You can take the create the dimension table with current information, only one row for basically distinct. Okay, so whenever they change it, they will definitely make a effective date, some date when they change the date, right? You take the maximum date by each row and take them, and now maintain the relationship like this one to many. This will become one to many, right? You can't go and take the distance between them and create a bridge table. That's not the process. You have to understand why there is a many to many. Is it because of some duplicates in dimension? Sometimes there could be duplicates, pure duplicates. You just need to remove the duplicates. You can't go and do all the procedure you learned. You can't go build bridge table. You can't do that. That's not the right way. So before, that's why I ask everyone to understand the tables, to understand the data, to understand business, and start building the reports, start building the models. This is one classic example, and so rapidly changing dimensions. What do they mean? They change very frequently. Let's say you are dealing the analysis for stock market. So let's take the stock price, stock name. So you have Reliance share at 10 a.m. it could be somewhere 1700. At 10:20, if more people purchase, if there is more demand, it will become 1800. If people started selling it, it will become 1650. I mean, if there is no demand, it will become 1650. It changes very frequently. Unlike SCD, slowly changing dimension, which changes once in a while, at very the change is very slow here. Here the change is very rapid. So you have to understand your dimensions. There are different other dimensions. We'll try to cover data warehouse concepts as well after this series, but you can go Meanwhile, you can go and read online. There are lots of stores available. You can go and read them if you want to master them. So these are the different dimensions and how what are the steps that you need to take care before you actually build the models. Now the last one is a cascading filters. What do you mean by cascading? Let's say you have two filters in your model. One is a country filter and another one is a state filter. If I select India in state filter, which is a filter, or a slicer in PowerBI language, okay? Sorry. I need to see only the states relevant to India, like Andhra Pradesh, Telangana, Karnataka, Tamil Nadu, Maharashtra, right? If I select USA, I should see like Texas, California, right? I need to see the US states only. Basically, cascading nothing but filtering one table, states table, based on countries table and show the relevant information. If you want to show them, how do you need to have? There should be a relationship. Otherwise, you can't filter it, right? If there is a relationship, it is very easy to filter it. If there is no relationship, and if you still want to filter it, how do you do that? That's a tricky one, right? Let's see with an example. I'll go back to the first model, our sales model. Here, there's a customer, product, and sales. So I'll add a new page. Okay, I added that customer, product, and sales, right? Customer and product sales. I already am able. Okay. So customers, I'll take a customer name, product. Ignore about the product names. It's a randomly generated dataset by Python, so they may not be meaningful. Okay, now this is, let's make both of them slicers. If I filter this, there is no effect to it because there is no movement to this table. There is no connection between these tables. Now you see the numbers are changing. If I select Ami owners, you see and again and all. If I select Andri, it is different. If I select Andy again, it is different. See, now this slicer is interacting with this because there is a moment, there is a filter moment. We are filtering this and we are depending on the fact table and filtering the product. So we by simply enabling bidirectional, we can filter it. Is it tough? No, but it could impact the performance. When you select something on customers to filter this, it has to go here, filter the big sales table, and that sales table filter should go and filter the product table, which is a lengthy process, right? Instead, the same way, and enabling bidirectional sometimes could lead to dependency errors, circular dependency or other dependency errors. So you may not be able to do that. In that case, you can do in other way. You can take any other attribute, like let's take price. We have price here. If we go here and now if I select something, it's not changing at all. You select anything, accept is the first, add is the next, and these are. If I select the price here, advanced filtering, not blank, apply. It's not changing. Let's do the same with a measure. Let me take the quantity and see any change. No, right? Let's take the measure. Sum of quantity. Let's take the same sum of quantity. I'll just use cascading sum of quantity. Okay. I'm wondering why it's not coming. I think I got the reason. Now you see it is getting changed, right? See, from this table, I'm taking one measure which is a quantity and I'm eliminating all the blanks, which comes, it is enable the relationship virtually. It is looking up whether everything is a blank or not here. It is building a virtual table and it is going there and filtering that. That is possible. But it takes more time because it has to split by that measure because it has to calculate that measure and split it. Instead of that, there is one more thing called a Boolean handling. You can create a Boolean measure. If I click here, new measure, these are my favorites. Booleans, I handle lots of calculation with Booleans. So not is empty, it's empty only, and fail sales is the fact table. Let me remove this. If I add this cascading here, it's not showing up. I think we did something mistake. Okay, let's convert this as an integer. That way it just checks the blank and it don't give you anything. Let's make it an integer. Now it works. Yeah, is 0. Now you see this, use the same measure, is 0. Now if you select something, it will filter that. It will filter that. It will filter this. How it is doing that? Basically, if you carefully look at this measure, it is going to sales fact table and checking if it is empty. So if there is any empty for the references, wherever we add this cascading. If it is empty, then it will give us a 1. We are looking for not empty, right? So it will convert them and this integer converts this true or false information into zeros or 1. Is empty is basically gives us the true or false as the output. Okay, then if it is not empty, then it will give us the zeros or 1 and we just need all the zeros. We come in here, we filter it. So I think it will filter unrelated. Yep. Now if you see, so whatever there is in fact table, we are filtering it. And if you see these values, they decreased it. They decreased by number because whatever the products, whatever the names that are not there in fact table, they are not coming up here. That's the one disadvantage. But you can with the measure or with the functions, right, with this boolean measure or with the quantity measure, that's one thing. What we are doing essentially, we are taking either, there are three ways. First thing is enabling bidirectional. It may not be possible sometimes. Majority of time I don't prefer bidirectional, I just go with the boolean measures, or take the other attributes like a quantity and all. If we do that, it has to create a summarized table behind the scenes. It has to split all these and cross check if the quality is not there or not. Instead, we are just checking if this reference is there or not by creating a boolean measure, which goes very simple, which executes very simple, right? I mean, very fast. So these are three ways, three distinct ways. You can create a measure like this and add it here. Sometimes you would need to do cascade in different way. People may ask, okay, do country and state cascading is one and name product cascading is three. There could be different sets of cascade. Let me go back to my notepad and explain. Okay, so there could be five filters. Filter one, two, three, four, five. So user may want to cascade these two as a set and these three as a set. Okay, if they filter this, it has to filter this. If they filter 2, it has to filter this. Here, if they filter 3, it has to filter both. If they filter 4, it has to filter these things, these two. If they filter by 5, it has to filter 4, it has to filter 3. For that, you will create one boolean measure and you will add in both the slices. This boolean measure and is 1. If you want to show the what are the values that are there in fact table. If you use this measure, you can create a boolean measure 2 or cascading 2 and you can put that in these three. These three will interact. If you change one, this will not interact with the three because you are not adding this. So by enabling directions, this may not be possible. These kind of scenarios may not be possible for few cases. So that's the cascading. So there are different ways. You can take the common attribute or you can simply change the direction. The best way is to use a boolean measures. So what is boolean measure? Just simply go not is empty and do this. If there is one fact table, that is fine. What if we have two fact tables? In this case, we have orders PC and products PC. How do we do them? Then simple. You just have to put an or condition double pipeline, give others fact table name. That's it. So if you have multiple fact table, here you need to write multiple times. You need to put an R class and write the condition multiple times. That works simply. So this way you can handle the cascading. If there is a relationship, you can do in this way. If there is no relationship, direct relationship, I mean, then you can use a calculation level. That's about cascading. And before we wrap up, I want to introduce you one other dimension, which is a date dimension. We have discussed many dimensions, but date dimension is a common dimension across any model. You take any models, 99.99% of the times there is a dates. There will definitely be a date dimension. And you have to create one date dimension if there is no date dimension. Because any business, you take any business, you analyze over time. You will estimate your business over the past to now and take decisions. Or you may predict your trends, future trends, again on dates, right? Future dates. So any business is analyzed over time for sure to take the decisions. And to do that, date dimension is a crucial one. If you don't have date dimension, it is very, very difficult to manage complex calculations, especially time intelligence calculations. If you want to use that without date dimension table, it will lead to complexity. I'll just start introducing one complexity with dates. Sometimes you may not notice the complexity in the table. It will be hidden. For example, let me show you one dates period table. It is difficult at times to understand that there is a flaw. There is some mistake. You see this? There's a worker ID. Okay. There's a date. There's a time to start, number of hours work, and the wage he got, the amount he got. If I want to visualize how many hours by month, okay. So if I go here, create a table, okay. I'll take a dates period, right? I'll take a month amount or number of hours worked. I think working hours will be simple. Okay. Now, if you look at this values, it may increase to 20. Now, in January, there is a 21 hours work. In February, there is a 41 hours. Let's go back to data and see that. If you see, let me arrange in ascending order. Now you see here, everything looks good, but there is some complexity hidden here. If you look at this ID, 31st January, he started work around 9. He worked for 5 hours. But when he ends the work, he ends around 9, 10, 11, 12, 1, 2. He end, I think I'm okay. Sorry, so I didn't switch it. So let me quickly explain you. So this is the dates period we have. This is the date dimension table we have. And if we analyze this over time, if I bring the month filter and number of hours worked, sum of the amount, I can see this. And you find no errors here. If we go to data, okay, this is date is there, time start is there, work is there. You don't feel that there is a mistake. But if you carefully notice, this worker 1 started on 31st January at 9. When he ends up the work, he ends up around 2 o'clock, which is next day. After 1, the date gets changed, right? So, these 3 out of 5, 2 hours is supposed to be calculated in February. But we are calculating them in January. If you see, sum it up, it will come to 21. We are calculating in January. In January, it is supposed to be 19 only, but we are calculating 21. That's a mistake. And same if you see, look at February. February okay. January it may not be a mistake. He started at in the morning. He ends up around afternoon. There is no mistake. Just look at the same example at February. He started around 6 o'clock in the evening. He ends up by 2 o'clock here. 14 means 2 o'clock. So 2 hours should go into March, but we are calculating in a February. That's a mistake. And we never realize that there is a mistake. Everything looks good. So there are lots of complexities. There are lots of hidden complexities with a date variable, which we will see in our next part of data modeling, where we will go with the date dimension, in detail date dimension, and the complexities of date dimensions, and few other scenarios. But I don't want to directly cover right after this session. I want to introduce DAX because there is going to be lots of DAX we are going to use with the date dimension to handle complex scenarios. I'll do the part 3 after the date dimension. So I will immediately start visualization and we can park DAX and this modeling and couple of scenarios that came from modeling. We kept on hold for hybrid models and hybrid tables and all for last session. We will discuss everything at the end of this series. So yeah, that's it about this session, and I hope you like this session. If you really enjoyed it, hit like and subscribe. That gives us more reach, helps us to do more quality and quantity of content. That's it from me. So see you all in the next video. Until then, keep smiling, be kind, spread love. Thank you so much.